Section 4.7, Area Between Curves. We have two objectives in this section. The first one is to use calculus to determine the area between curves, and the second one is to solve applications involving area between curves. So let's start with the first objective, which is the area between curves. How do I find the area between two functions, f and g, which are continuous, where f of x is greater than or equal to g of x, meaning f of x is the upper function and g of x is always lower than it, it's always underneath it, on the interval a to b. Well, it turns out all I have to do is solve this integral, the definite integral from a to b, and we just put f of x minus g of x inside, and we integrate everything with respect to x. So now let's talk a little bit about why this is true. We know from a previous section that if I wanted to know the area underneath the function f and the x-axis from a to b, so it's basically this full area over here, if I want to know that area, what am I required to do? Well, it turns out that I'm required to just find the integral from a to b and integrate the function f of x with respect to x. So that would be the area in yellow, right? So if I want to know the area in yellow, that's all I have to do. But again, if I want to know the area underneath the function g of x, between the function g of x and the x-axis, and the lines from a to b, so if I want to know this little area over here, then using the same knowledge from a previous section, we can say that the area of this section, or the area of this region, is again an integral from a to b, but this time we integrate the function g of x with respect to x. So therefore, if I wanted to know the difference between those two areas, if I want to know the space between the f and the g function, which is this section over here, this region, then all I have to do is take the larger amount and subtract from it the smaller amount. This would be the yellow minus the green. And because both integrals have the same bounds from a to b, and we're integrating with respect to x in both cases, combining this integral minus that integral would result in the formula that we have in the middle of the page. So now let's take a look at example 1, now that we know the formula for finding the area between two curves. It says to set up the integrals to find the indicated areas, but it tells us that we don't need to evaluate the actual integral, so it just wants the setup. And for part 1, we're looking for the area of the region bounded by the function y equal to x squared plus 2, the function y equal to negative x, and the lines x equal to 0 and x equal to 1. So let's begin by first getting an idea of what the graphs look like. For the y equal to x squared plus 2, we know this is a parabola. It's going to cross the y-axis somewhere at 0, 2. And so it's a parabola, so it's going to look like a U shape. And I'm only going to draw the answer, or I'm only going to draw the function in the first quadrant. I'm not going to draw the full parabola because we're only interested in what's happening between the lines x equal to 0 and x equal to 1. Now, the function y equal to negative x is a line, slanted line, passing through the origin, and it has a negative slope, so I know that the graph kind of looks something like this. So this is the graph of y equal to negative x. It just points down, and it passes through the origin. And now keep in mind that we're going from x equal to 0, so this is this place, this is this vertical line, all the way to x equal to 1. So let's pretend like this is x equal to 1 on the x-axis. So we want to know how much space there is here between the two curves and the x-axis. Sorry, between the two curves and the vertical lines x equal to 0 and x equal to 1. So how much is this gray area? Well, according to the formula, the area that we are searching for is some kind of an integral. And for us, the starting point is x equal to 0. So that's going to be the lower bound. So we can either write x equal to 0 or just put 0. All the way to x equal to 1. That's where we're stopping. That's the stopping point. So that will be the upper bound. Now, all we have to do now is determine which is the upper function, which is the lower function on the interval that we're working with. So between 0 and 1, what's the upper function? Well, the one that is higher towards the top of the page is the y equal to x squared plus 2. So that one goes first. The rule or the formula tells us to subtract the lower function. So what exactly is the lower function? Again, on the same interval from 0 to 1, the lower function is this one. It's the negative x function. So we're supposed to subtract that. So be careful here. There will be a double negative situation going on because the formula gives us this minus sign, but the lower function is itself negative x. So that's the reason why we have a double negation. So in other terms, what we're saying is that if you want to know the area in gray, all you have to do is find the integral from 0 to 1 of x squared. Minus is going to be a plus x. Then there's the plus 2. And it's all being integrated with respect to x. Now, for now, this is all we need to do because they just said set up the integral but don't actually solve it. Obviously, we know how to solve this, so I'm only going to do it for this first one. I'm just going to continue, even though this is where I need to stop for this problem. But I just want to finish the rest of the problem and see what we get. So x squared gives us x cubed over 3. The antiderivative for x is x squared over 2. And finally, the antiderivative for 2 is just simply 2x. And we're integrating all this between 0 and 1. And the fundamental theorem of calculus tells me that I need to plug in the upper bound first, then the lower bound. So when I plug in 1, which is the upper bound, into all of the x's, I would get 1/3 and 1/2 and 2. And when I plug in 0 into all the x's, I just basically get 0. So the answer is going to be 1/2 plus 1/3 plus 2. And we can see that the sum of these numbers is 17/6. So keep in mind that for this problem, we don't have to do these additional steps. We need to stop once we set up the integral. But for the future problems, we will have to continue and do the rest of the problem and finish until we have the final answer. So this is what it would look like basically. Now moving on to part 2, this time we have the function y equal to x squared and y equal to 6 minus x. However, we're not told the left and right boundaries. We're just given some two functions. So that means they probably are crossing each other. So let's start by graphing them. So first of all, y equal to x squared is a parabola passing through the origin. So it's going to look like a U shape. So this is what my graph would theoretically look like for y equal to x squared. And for the 6 minus x, my graph is going to be a line because of the x to the power of 1 that's there. It has a negative slope, so I know my line is going to be pointing down from left to right, and it crosses the y-axis at the point where the y would be equal to 6. So I'm thinking something like this, and this point, like we said, is the point 0, 6. So this is the graph of y equal to 6 minus x, and we're looking for the area between the curves. So basically we're looking for, again, this region's area. So how much space is in the gray shaded area. Now the difference between this problem and the previous one is, like I said, they're not giving us the place where we should stop on the left and on the right. So we ourselves have to find where the two curves are crossing each other. So at which location is the crossings actually happening? So we need to determine that. And how do we do that? To determine the places where the functions intersect, we will basically say that the y's are equal at those locations, and we will set up this equation. So to find the intersection points, so to find the intersection of the two curves, we will say that we want the y1 to be equal to the y2, where y1 and y2 are the given functions. So we want x squared to be equal to 6 minus x. And when we solve this equation, we should hopefully end up with two x's indicating where the region that we care about starts and where it ends. Now to solve this equation, it's beneficial to put everybody on the same side, make it all equal to 0, then try to factor the quadratic. I want two numbers that multiply to -6, but when I add them, I get a positive 1. So I'm thinking probably 3 and 2 will get the job done as long as I make the 2 negative and keep the 3 positive. And you can verify 3 times -2 is -6. And when you add the 3 with the -2, you get a positive 1. So my factored form would be something like x plus 3 times x minus 2 equals 0, which means either the x is equal to -3 or x is equal to 2. So those are my intersection points. Those are the x-coordinates of the intersection points. And so one of them is negative and one of them is positive. So I know that the left one is going to be the -3, and the positive one is going to be just simply 2. Now that we have the intersection points, we can finally set up the integral. So the integral is going to be the integral going from a to b, where a is -3 and b is equal to 2. And we need to know on the interval that we care about, what is the upper function and what is the lower function. So we're going to ignore everything that's happening on this side. We're going to ignore everything that's happening on that side because those are not inside of our interval. And we are going to just focus simply on the middle interval. So in the middle interval, who is on top and who is on the bottom? Who's towards the top of the page and who's towards the bottom of the page? Well, it seems like the red function is on top, so I'm going to put that one first. And then the formula tells me to subtract. And what is the function on the bottom? Well, it's the parabola, so I will be putting x squared afterwards, and then just putting the dx at the end. So the area formula, or the area integral, will be -3 to 2, 6 minus x squared with respect to x. So this is how the setup would look like, and obviously I'm not going to solve the rest of the problem because they said to just set up the integral, but don't actually solve it. Now, let's take a look at the calculator and see if the calculator can help us finding these numbers right here, the 3 and the 2, or rather the -3 and the 2. So to do that, we're going to go to our calculator, and on the first line on y1, I'm going to write the x squared function's name. And on the second line, I'll be putting 6 minus x. I'm going to click zoom and then 6 to see the full picture. And now I see the parabola and the line that I graphed by hand. There's a lot of empty space on this graph, so we can try to get rid of some of it if we wanted to by going to Window and modifying some of the numbers here. So for instance, I can just go from -5 all the way to 5 on the x-axis. And for the y-axis, I'm going to just start at 0 and just take it all the way up to 10. Seems like a good number. And we'll just click Graph, and we now have a little bit more zoomed in view of the region we care about. Now, ideally, I'd like to know the intersection points. So to do that, using the calculator, I'm just going to click second and then the trace key. That puts me into this menu called Calculate. And there's a bunch of options here that we can select from. I'm going to be choosing option number 5, which is called Intersect. So once you select number 5 on your keyboard, your calculator should be blinking somewhere on one of the curves, depending on which one you put first. For mine, it's blinking down towards the origin. You can sort of barely see it, but it's asking me for the first curve. To show it better, I'll just use the left key to show you the little blinking cursor. So all I have to do now is just tell the calculator what my first curve should be. And it doesn't matter for the intents and purposes of what I'm doing, which one is called the first curve, which one is the second one. So I'll just click Enter and select this one as my first curve. So the parabola is the first curve. Now the calculator wants to know what is the second curve. And you can see the blinking cursor is now on the red line. So I'm going to click Enter again. And now it says Guess. So this is what's important here. Since there are 2 intersection points, I'm going to take my cursor and move it to the intersection point that I would like to find. So just get it close enough to either the left intersection point or the right intersection point, depending on which one you want to find. So right now, I want to find the left intersection point, so I'm going to get my blinking cursor as close as possible to that, and then just click Enter. And you can see the intersection point at the bottom of the screen. It says -3 and 9. So it gives me both x and y coordinates. So it seems like the actual point on the left side is -3, 9. This is the actual coordinates, and that's where I'm getting the -3 from, by the way. Okay, so let's do it again for the other intersection point on the right. So how do I find the other intersection point? Again, I click second, trace. And then again, I select option number 5 for the intersect. It's asking me for the first curve, and right now everything is in blue, so I'm sitting on the blue curve. So I'm just going to click Enter. And now it's asking for the second curve, and you can see all the colors now change to red. So again, I'm going to click Enter to select the line as my second curve, and it says Guess. Now, if I hit Enter right now, it's always going to return -3 because it's closest to the left side. So I don't want -3 again. I want to see the 2. So what I have to do for that is just use my right cursor and just click it a few times and get my little butterfly closer to the other side. So this way the calculator will calculate the intersection point on the right instead of the one on the left. And once you click enter, you should see the intersection is 2 with the y-coordinate being equal to 4. So according to the calculator, this point here has coordinates 2, 4, and that's where I'm getting my 2 basically from. So you can either solve it manually, and that's the ideal option, or you can confirm that you solved it correctly by doing the steps that I just showed you. Okay, so now that we know how to do all this, how to find the intersection points and how to set up the integrals, let's take a look at example number 2, where we're told to set up and then evaluate the integrals. So we have to do the full problem. And we want in part 1 to find the area enclosed by the curve y equal to x, square root of x, and then the line y equal to 1/4 of x. So you can use your calculator to help you with the graphs of these functions, but we should, in theory, know that the square root of x is some sort of a graph that looks like it starts at the origin and then it goes towards the top right of the page. And we know that 1/4 of x, the curve there, has x to the power of 1. So that makes it into a linear function. So that means that the graph should be a line. And the line is, in theory, passing through the origin and going towards the top right side of my page. So this is the line 1/4 of x. And they want the area enclosed by these two curves. So enclosed by these two curves just means that it's surrounded by these two curves. The only area that's surrounded by these two curves is the area in there. So basically, I'm searching for the area of this region over here. We know that the intersection is happening at 0 for the two curves. They both pass through the origin. So we know that that point has coordinate 0, but we don't know where this second coordinate is going to be. So what's the number there? You can try to guess the number, but it's always better to just do some math and use algebra to determine what the value is. We can also confirm that we have the right answer by using the calculator afterwards. But let's begin by finding the intersection point. So how do I find the intersection of the two curves? Well, I take the first y and I set it equal to the second y. So in my problem, this is the first y and this is the second y. So in other terms, I'm saying I want the square root of x to be equal to the second curve or the second equation, which is 1/4 of x. So you got to solve that equation somehow and get the x values. To solve this type of problem, it's usually recommended that we start by squaring both sides. And the squaring is done to get rid of the square root, because square root of x squared will just simply be x. Now, on the other hand, 1/4, when you square it, it will become 1/16, and x squared will be just simply x squared. So that's how we start off this process. This is some sort of a quadratic. To make my life a little bit easier, I'm going to multiply this side by 16 and multiply this side as well by 16. That way I'm avoiding the fractions. So I'll just do that mentally. So it will be 16x equal to x squared. And because it's a quadratic, it's usually beneficial to put everyone on the same side. So I'm going to take the 16x and move it over there. That makes it negative 16x. And in its place, there's nothing left. So I'm going to write equal 0. So now we can use some factoring, and I'm using the factor using the GCF method to factor out the x. So that means either x is 0, which I kind of already knew, right? That's this point over here. We predicted that from just our previous knowledge. And the second point is x equal to 16. So is this the right number that needs to go there? In theory, it should, but let's confirm. What's the square root of 16? Square root of 16 will be 4. And what's the 1/4 of 16? So 1/4 of 16 is also equal to 4. So it seems like we did everything correctly. And so we have the final answers that we need for the left and right bounds. So this part of the problem, the intersection point, has to be done somewhere. It needs to be shown. Now you can use your calculator to confirm. So let's take a moment here to check with the calculator how we can do this and repeat the steps that we did previously. So on my calculator, I'm going back to the Y menu where I graph everything. And for the first line, for the y1, I'll be putting the square root of x equation. On the second line, I'll be putting 1/4 of x. And if I click on zoom 6, you'll see part of the region that we care about. So we don't see the full region. We're seeing a lot of empty space. So let's modify the window a little bit. How can we modify the window? We can either do it manually by clicking window, or we can go to zoom and tell the calculator to figure out the best zoom for us. And we can do that by just going from the bottom and clicking zoom fit. Zoom fit will allow the calculator to kind of decide for us what's the best window. It's sometimes great, sometimes it's not so good. So let me see. If I click zoom fit right now, the calculator does not show me the full region. It kind of zooms in on part of the graph, but I'm still seeing a lot of negative x values that I don't really care about. And I'm not seeing the second intersection point on the right side. So I'll have to do this manually. So I'm going to go to my window. And like I said, I don't need to see all these negative x coordinates. My blue curve starts at 0. So you know what? Let's start with x minimum at -1. For my x maximum, usually it requires a little bit of guess and check. I'm going to start with 20. And for the y minimum, again, I don't need to see a lot of negative y values, especially because the graph on the page did not show me a lot of negative y values. So again, I'll be putting it at 0. And for the y maximum, again, it requires a little bit of guess and check. So for now, let's just put 10 and see what happens. So when you're ready, click on graph, and we should be able to see the full graph. Turns out that I don't need to go all the way up to y equal to 10, so I'm going to go back to my window and change the y maximum from 10 to, let's say, 6. There's no right or wrong answer for this part of the problem. It's just you and your preference. What do you want to see, and how much of the empty spaces do you care to see? But now that we have the two graphs on this first quadrant, we'll go ahead and click second trace. That will put us in the calculate menu. And again, just like before, we're going to click option number 5 on our keyboard for intersect. And then decide what's the first curve. Yep, I like the blue one. What's the second curve? I'm going to select the red one. And it wants to guess, but I need to first tell it, okay, go to the first one, even though I kind of know it's 0. I'll just put it close enough to 0 and just click enter. And I wasn't close enough. It jumped to the other side. It told me that x is 16. That's great. I got the second coordinate instead of the first one. But let's do this one more time. So I'm going to click second calculate, and then click option number 5. It wants the first curve. I'm going to select the blue one. It wants the second curve. I'm going to tell it to go to the red one. And finally, guess. So I need to get my cursor super, super close to 0. Otherwise, it's going to, again, jump to x equal to 16. So let's go a little bit further. And this requires just clicking the right or left key multiple times. Okay, I'm ready to go, so I'm just going to click enter. And again, it's jumping there. So why is that happening? That's happening as an artifact of how the calculator graphs the square root of x. And we're putting the starting x value at -1. We're putting the starting y value at 0. So it's not going to be able to find 0, 0, basically. We'll have to modify the window a little bit, but I'm not going to do that for now. We already know that 0 is an intersection point. So let's just continue with our problem. It's quite obvious that 0 is the point because square root of 0 is 0, and 1/4 of 0 is as well equal to 0. The calculator is having a hard time finding that value, and that's again why we always rely on the algebra to give us the answer. Then we confirm with the calculator to just make sure that we didn't do any silly mistakes. Now that we have the intersection points, though, we can look for the area in this problem. So the area in this problem is going to be an integral, and the integral starts off at 0, and it goes all the way to 16. These are my lower and upper bounds, and we found them the old school way by doing just a little bit of algebra. And the area wants the upper function first. So ignore everything on this side, ignore everything on this side, and just focus on the region in the middle, the region that you've selected. On that region, what's the upper function and what's the lower function? So which one is the one closer to the top of the page? Well, it's the blue curve, which is the square root of x in our case. Which one is the lower function? Which one is the one closer to the bottom of the page? Well, it's the line, and the line is 1/4 of x. And we always integrate with respect to x in these problems because the given equations all have x. So this is my setup. And normally I would put a box around this thing and move on. But in this case, in this problem, they want us to continue and find the actual area. So let's continue and start by first rewriting the square root of x as x to the power of 1/2. I need to do that because I want to add 1 to the power and divide by the same value later on. So it's helpful to know the power. 1/4 of x is just chilling for now and hanging out over here. And so now that I'm ready, I can start integrating. What's the antiderivative for x squared? X to the 1/2. So we need to add 1 to the power and divide by the same thing. Well, x to the 1/2 plus 1 is just going to be x to the 3/2. And I'm supposed to divide by 3/2, but we don't like to do that. So we'll just flip it upside down in our head and write 2/3 on the front. And for the 1/4 of x, what's the antiderivative? Well, the 1/4 is just going to go for the ride. X in this case has power 1, so we add 1 to the power and we divide by the same thing. So it's actually going to be x squared over 2. And there's a multiplication between them, so I'll just write negative 1/8 of x squared directly because 4 times 2 is really 8. Okay, and my fundamental theory of calculus says you're supposed to plug in the upper bound and lower bound next, so I'm getting ready to do that next. So let's continue and plug in the upper bound. So 2/3, we get the upper bound 16 to the power of 3/2 minus 1/8 16 squared. So this is the value I would get if I plugged in the upper bound. Then I need to plug in the lower bound. The lower bound is going to be 2/3 times 0 to the 3/2 minus 1/8 0 squared. Okay, so this is a direct application of the fundamental theorem of calculus. Now, the second bracket is just going to be all completely 0. 0 to any power is going to be 0, and 0 squared is going to be 0. So multiply 0 by 2/3 or by 1/8, it does not matter. The whole thing is just simply 0. So that whole thing is going to be 0, so I'm going to ignore it. And all I have to do is focus on the first portion. And we can actually use the calculator to give us some sort of an answer. So let's go to our calculator screen and go to the main screen and type in the expression that we were working with. So 2/3 times 16 to the power of 3/2. So in my case, I need to put parentheses with the 3/2 surrounded by the parentheses. If I don't put the parentheses, then the 16 will get cubed, and then the full answer so far will get divided by 2. But I don't want that. I just want the power to be 3/2, so that's why I'm putting the parentheses around the 3 over 2. The second part is 1/8 of 16 squared. So for that part, I'll just do it this way, 1/8 times 16 squared, and I'll just click enter. I'm seeing a decimal on the screen. There's a chance that we can turn it into a fraction. Let's find out. We can click math 1, and we got lucky that the answer was turned into a fraction. If it wasn't possible, if the calculator couldn't do this step, we would have to go back to the paper and solve it the long way, squaring everything, cube rooting everything, or cubing, or whatever, depending on the problem, to get an exact solution with square roots and cube roots and so on and so forth. But in this case, we got lucky that the answer is 32 over 3. So that's my final answer, and I am basically done with this problem. Now moving on to part 2 of this problem, it says find the area enclosed by y equal to e to the power of 2x, y equal to 1, x equal to 0, and x equal to 3. So my functions are basically these two, and x equals 0, x equal to 3 are just basically the borders on the left and on the right. But it may be difficult for you to graph y equals to e to the power of 2x, so you can use your calculator to do that. It's not wrong, so let's go ahead and do this with the calculator. E to the power of 2x first, and I'm going to add the second function, which is just y equal to 1 to my graph, and I'm going to click zoom 6 to reset the graph, and this is what I'm seeing. So again, I'm seeing a lot of empty spaces on the bottom. I'm seeing a lot of the second quadrant as well. I don't need to see all that. I need to focus on what's happening between 0 and 3. So I'm going to click on my window and tell the calculator that my x minimum should be -1, and my x maximum, let's make it 4. This way, the interval that I care about, 0 to 3, will be kind of in the middle of my x-axis. For the y minimum, for now, let's just start with 0 and go all the way to 10, and we can modify the y maximum in a second after we take a look at what's going on the graph. So this is my graph, and it looks kind of pretty. I'm satisfied with how this looks, so I'm just going to stop here and copy it to my calculator. So to help me out a little bit, we can trace a couple of points. So I'm on the blue curve now. I'm going to trace what happens when x is equal to 0, and obviously we see that the y-coordinate is 1. This is the intersection point between the two curves. They both intersect at 0, 1. And I'll use a second point on the blue curve. So I'm going to say, what is the y value when x is equal to 2? So when x is equal to 2, I can see that the y value is 54. That's way too big. So let's try another one. Let's trace x equal to 1. And you can see when x is equal to 1, the y is 7.38. So roughly around 7. So I know that my blue curve, my y equal to e to the power of 2x, will kind of look something like this. It's going to exponentially grow as I go towards the right side of the page. And the other curve just passes through the same point on the y-axis, but it's always horizontal. This is y equal to 1. It's a horizontal line. We know that this is the first intersection point, and that's why they said x equal to 0. They want us to start here at this intersection point, and they want us to stop at x equal to 3. So I'm going to pretend like this guy here is x equal to 3. And so if this is my second intersection point, the region that is enclosed by the curves and the left and right intersection point will be this region. So we want to know how much area there is inside of that shaded region. We don't have to look for intersection points in this problem because we're told the start and the end of the region. So we're going to go directly into area equals integral. The starting point is 0. The endpoint is 3. So these are also the lower bound and the upper bound. So the upper bound was given to us, and the lower bound is also given to us. So that's great. That saves us a lot of time. And now we have to decide who's the upper curve and who's the lower curve. So again, ignore everything here on this left side, ignore everything on the right side there, focus on the middle part, the one that you shaded. On that shaded portion, which curve is towards the top of the page? Well, it's obvious, it's the blue one, it's this curve. So I'm going to write e to the power of 2x first. And I need to subtract from it the lower curve. And by process of elimination, the lower curve is just the 1. And we're integrating everything with respect to x. So it remains to just integrate this problem. So let me get rid of all the colors before we start integrating. So this is the integral from 0 to 3, e to the 2x minus 1 dx. Turns out that for this integral, e to the power of 2x, I need to use a u-sub. So let me go to my Scratch work. So here's my Scratch paper. I'll just integrate e to the 2x on the side real quick to see the answer for it. We don't have a formula for that, but we know that we need to make a u-sub. We talked about u substitution in a previous section, and we said that when you have an exponential, usually the u is the power of the exponential, the power of e. The du is going to be 2 dx, and so do I have everything I need for this du for me to be able to integrate using the substitution method? So let's see, I have the dx, it's ready to go, but I'm missing the 2. So I'm missing the 2, so how do we fix it? You may recall that we just put a 2 there, and we put 1/2 on the outside. So with this in mind, we can now write 1/2 integral of e to the u, and both the 2 and the dx together will give me the du that I need. Oops, I jumped. and I'll get the du here. So we've got the u, we've got the du, and now what's the antiderivative of 1/2 e to the u du? It's 1/2 e to the u plus c, where c is just some kind of a real number. But we need the answer in terms of x, so we're just going to say, well, what was u in the first place? Well, it actually was just 2x. So the answer for the antiderivative for e to the 2x is just 1/2 e to the 2x, basically. So this is scratch work. You can do that off to the side, but it's not part of the main problem. And I'm doing it because I want to know the antiderivative for e to the 2x. So according to the scratch work, it's e to the 2x. And technically plus c, but I'm not going to write the plus c here because I'm dealing with a definite integral this time. So I'm just going to get rid of the c and just integrate the -1 next. The antiderivative for 1 is just simply x. And we're integrating between 0 and 3. So according to the fundamental theorem of calculus, the upper bound is supposed to go in first. So I'll plug in the 3's into all the places where I see an x. Then the lower bound goes in afterwards. So I'll plug in the 0 into all of the x's. Okay, so let's wrap things up with 1/2 e to the power of 2 times 3 is going to be e to the power of 6 minus 3 minus 1/2 e to the 2 times 0. 2 times 0 is going to be 0, and so e to the 0 is going to be just simply 1. So the e is roughly 2.7. 2.7 to the power of 0 is just going to be 1. So 1/2 times 1 is going to be 1/2. And finally, minus 0, well, that's just 0, and I'm not going to write it. So ultimately, my answer is just 1/2 e to the 6, and whatever I get from adding -3 and -2. So -3 minus 1/2, not -2, not minus 1/2. I'll need a common denominator, let's say 2. So that's going to be -6 minus 1, so -7/2 is my final fraction. So this is the final answer, and let's confirm that our answer is correct by plugging this portion into the TI calculator. So to do that, we'll go ahead and go to the main screen of my calculator, and we'll click on Math, then option number 9 for FNIT, and we want to integrate e to the power of 2x. So I'll type in e, which is second, then I click the ln key. That will put e on my screen. And then I need to put 2x. I need to tell the calculator this is the end of the power, so use parentheses. Minus 1, and we're integrating with respect to x from 0 all the way to 3. My answer is 198.21. If I try to convert this into a fraction, the calculator will not be able to do this, obviously, because we had an e to the power of 6 in our answer. We know it's an irrational number, so there's no way for the calculator to convert it into a fraction. That's by definition what an irrational number is. It cannot be converted to a fraction. So you know what? Let's just confirm by putting in our answer. So 1/2 e to the power of 6 minus 7/2. This is what we discovered by doing it the long way. And when I click enter, I want to see 198.214396.7. And I do. So that confirms that my work was correct. And this is how you can check your answer during exams or quizzes or even on the homework. The final problem that we have in the section is a little word problem. It tells us that a factory selling Bluetooth speakers has marginal cost function given by C of x, and you can read the rest of it, where x represents the number of speakers, and the marginal revenue function is given by R of x equal to so on and so forth. They want us to find the area between the graphs of these curves and x equal to 0. Okay, and then they're asking, what does this area represent? So to begin with, I'll go ahead and go to my calculator and graph the function c of x and r of x and decide who's on top, who's on the bottom. I also need to know the intersection point, so it seems like the two curves are intersecting because they're only giving me one of the boundaries, which is x equal to 0. So let's swap over to our calculator and first go to the Y menu and type in the cost, 0.02, We have x squared there, minus the x, and plus the 250. For the marginal revenue, we have 1450 minus 3x. So I'll go ahead and click zoom 6, and obviously I won't see anything. I know that one of the numbers has 1450, one of the functions rather has 1450, so I know that the y's are probably going to be very, very high. So you know what, let's click on zoom, and this time I'm going to tell the calculator to decide the best fit. So I'll select zoom 0 for zoom fit, and this will tell the calculator to decide what's the best window to show me, and then we'll go from there. So once you're ready, just click enter, and the calculator will show now two curves. There's a red curve and there's a blue curve. The red curve represents the revenue, or the marginal revenue rather, and the blue curve is the marginal cost for me. So this is what my graph looks like, and obviously I'm not happy with how this looks. So let's modify this window a little bit. So first of all, I don't need to see any negative x coordinates because x represents the number of speakers and we can't have negative values. So I'll go ahead and swap my window to start off at 0. And let's see, I don't know what x maximum I need for now. Let's just go with 50 and see what happens. So I'm seeing a little bit better, but it looks like the graphs are going to intersect somewhere to the right still. So we can keep modifying this as many times as we want. I'll just jump straight to 300 and I'll just, maybe it'll be an overkill, but let's see. Now I'm seeing the graphs intersecting, so that's great. That's kind of what I want. The other thing I want to do is go back to my window and switch over the y minimum. I'll put that at 0 so we can see the x-axis basically. And there we have it. This is the perfect graph that we could have asked for. Now, we know that x equals 0 is an intersection or a boundary. That's the y-axis basically. So they want us to look for the area between the curves and the y-axis. So I need to know where the two curves intersect one another. To do this by hand, it might take a little bit of time, so let's just ask the calculator for the intersection point. So we're going to click second trace and use option number 5 from the list, which is intersect. The calculator is going to want the first curve. It doesn't matter which one you select. I'm going to click enter. It wants the second curve, and again, click enter. And it's asking, should I guess? I'm going to get it as close as possible to the intersection point. This will allow the calculator to find the intersection point quickly, and it will find the intersection point to the right side here. And we can see the intersection is happening at x equal to 200, y equals to 850. The only thing that matters from this whole thing is the 200. So let's go to our page and start by writing the integral. So the area between the two curves is the integral going from 0 because they told me to start at 0. They didn't tell me where to stop. I had to find it myself, and we decided that the stopping point should be 200. So how did we get it again? Using the calculator. Now, which one is the function on top and which one is the function on the bottom in this problem? So going back to my calculator, the red line seems to be on top, right? In this whole region, the red line is on top. And the red line is the marginal revenue equation, which we're calling R of X in our problem. So I'm going to put R of X first. Then I'll be putting the C of X afterwards. So now let's go ahead and replace the R of X and the C of X with the actual values. So R of X is 1450 minus 3x. The C of X function is 0.02 x squared minus x plus 250 with respect to x. So let's see. Let's first get rid of the minus by distributing it to the second parentheses. So we'll do that next. So 1450 minus 3x. We can safely remove the parentheses there because there's nothing in front of the whole expression. But the minus sign here needs to go to everybody in that second parentheses. So we'll get negative 0.02 x squared minus x is going to be plus x. And finally, minus the 250 with respect to x. Now, if you'd like, we can combine this and this. They both have x's in them. We can also combine the 1450 with the negative 250 because they're both regular numbers. This way, we're integrating only 3 terms rather than 5. So let me do that next. So the integral is from 0 to 200. The negative 0.02 x squared does not have any friends, so I'm just going to write it first. Now, negative 3x plus x will be negative 2x. And finally, the last thing we have to do is calculate the 1450 minus the 250, which will give us 1200. And this is all being integrated with respect to x. Now that we've cleaned up the expression as much as possible, we can go ahead and combine, or rather integrate. So what's the antiderivative for negative 0.02 x squared? It's going to be negative 0.02 x cubed over 3. Or you can put the 3 underneath the 0.02. It does not matter. It's your choice. You can decide whatever you want to put it. Now for the negative 2x, the antiderivative will be negative 2x squared over 2. But then, you know what? Let's just get rid of the 2's and just put x squared. Simplify the expression right away as we go. And finally, the antiderivative for 1200 will be 1200x. And we're integrating this between 0 and 200. Now notice that when I put the 0 into the expression, into all of these x's, the answer is going to be 0. So there's not going to be anything useful there. So I'll just worry about the 200 to save a little bit of time. We'll just plug in the 200 into the expression and not worry about the 0. So we're going to have 002 times 200 cubed rather than squared, and minus the 200 squared, and finally 1200 times 200. To wrap things up, we'll just put this into a calculator and get the final answer using the calculator. It's too tedious to try to calculate this by hand. So swapping over to our calculator, we'll just quit this graph, and I'll go ahead and type in the expression that I care about, which is negative 0.02 divided by 3 times the 200 cubed, 200 to the power of 3. There we go. And minus the next term was 200 squared. And finally, I had 1200 multiplied by 200. So the answer is 146,666.666 and so on and so forth. So let's just transfer this to our page. So 146, and then 3 more 6's, and then it continues forever, 6, 6 forever. And if we wanted to, we can convert this to a fraction by clicking Math 1, and it will be 440,000 divided by 3. So it's more appropriate to probably write that answer, 440,000 divided by 3. This is an exact value. It's better than any decimal that we can get. So that's why I'm going to leave my answer in this format. Just let me make sure that we got the right numbers, 44 and then 4 zeros. And so, yes. Now, what does this number represent? This basically represents the net profit for the 200 speakers that were sold. And before we wrap this section up, let's go ahead and type this whole thing into our calculator and see if we actually did the problem correctly. So to do that, we'll go to the main screen of our calculator, click Math, then option number 9, and we'll type in all the expressions as given. So 1450 minus the 3x was the upper function. Then we subtract the lower function, which is 0.02 x squared minus x plus the 250. I'm going to tell the calculator that I'm integrating with respect to x, and my lower bound was 0, provided by the problem. The upper bound was 200, which was something we found using the intersect command on the calculator. And if we hit enter, we see the same solution. And if we want to convert it to a fraction, we just click Math 1. And again, it is the same exact fraction that we got by doing the long work. So remember, this number that you're seeing on screen represents the net profit for the 200 speakers.